Dear all, good morning. Now our lecture is least squares approximation. In this lecture, we are discussing what is the least square approximation, or you can say least square solutions, or best approximation, or best solution. So in this one, generally we are using this least square approximation for a fitting a curve or a line for given data. For given data, what is the best line or best curve? That's what is the best approximation. So in this one, first generally take suppose this system Ax equal to b has no solution. When it's possible, no solution. It's possible. It's possible when the system has when it's possible when the system has more equations than unknowns. More equations. When the system has more equations than unknowns, the system has no solution. No solution. For suppose take A is on m by n matrix. That means equation is more means m greater than n. That means equation is more than unknowns. That means suppose take matrix. Yeah, that means each one is column. First column, second column. Up to how many columns are there? M rows and n column. That means n columns am into x vector equal to b. Suppose this x vector x1, x2, and so on xn. This system has no solution means suppose this system is solution means the b is lies in the column space of matrix A. That means B is the linear combination of these columns. It's lies in. It's not solution means the B is not lies in that column space. Now observe here this point. See, it's a system has more equation. This m by n matrix. Here the column space, the n columns span a small m dimensional space. M dimensional space. See, we are taking suppose n columns are linearly independent. This n columns is span a m dimensional space. It's a small one because m is more than n. That means this system has no solution. See, when that system no solution, that means B lies is outside. Suppose take any vector. Suppose take B is outside. B vector is outside. So now we have to solution means you have to convert to B is closer to B is in the column space. Convert to column space. That means you have to project to B2 in the column space. This is the column space. How to project? So suppose I take suppose a projection of B is some vector. Okay, we are taking projection. This is P is equal to A x hat. Already we discussed last class. This one. Suppose this is the B vector. Now projecting this one. Project this one. We get when the projected to up to in this one P, we get error vector. This error is B minus P. See, now this it makes some angle. This is a right angle triangle. Okay, this one. See now here, see, now we have to convert to B is in the column space means the error is must be 0. But this is not always possible. That's why this system has no solution. Its a solution means we have the error is 0. Error is 0. Here this x hat, this means we are this projection is closer to B. When it's project closer to B, this is approach to 0. That means you have to approach to 0. When it's possible, this x hat, where this x hat close to as ax hat as close to B vector. When that this ax hat close to B vector, that ax hat means it's a projection. This means ax hat equal to projection of B on column space. This is the AX hat. Yeah, we are using the small p. This is a projection. So now it's close to. That means this is called, when is the this x hat closer to b. When the x hat closer to b, this is close to b. This x hat is called. This is a solution of this one. Is least square solution. Least square solutions or least square approximation. This is the one. See, last class we discussed this one, column space. We know that a column space, matrices are columns, A transpose and this error vector B minus AX hat equal to 0. This is orthogonal. That means that B minus AX hat. What the B minus AX hat error vector? This is lies in left null space, any A transpose. Left null space. We know this column space and left null space are orthogonal. This is orthogonal. Which orthogonal means if you take this one, that A transpose B is equal to A transpose A X hat. The last class we proved, but in place of B, where I am taken vector is B. Generally, we are using system X equal to B. That's why I am taken B in transpose A. See now, this one. A transpose A X hat equal to A transpose B. This is called is a normal equation or fundamental equation. This is a normal equation. See now here x hat is minimizes. This x hat is minimizes error vector. This norm, that length is minimizing this one. That means norm of minimizes this one b minus ax hat. This x hat is, that way this is the least square approximation or least square solution. Least square solution. So now how to find this one? Already we discussed this one, finding this x hat. See, whatever given system, this ax equal to b, the system has no solution. No solution. The system has no solution. Multiply both sides. Multiply with A transpose. We get A transpose A. Now take AX hat equal to A transpose B. So this system has a solution. We are not get exact solution. If it's exact, is maybe it's a best solution we are getting this one using this system. A transpose A X hat equal to A transpose B. See now, here B is how to project into in that one. B vector. See, when you are projecting B vector in that column space, that means when the error is approach to 0, the B is lies in the column space. When the vector is lies in the column space means the system has a solution. When it's possible by projection. That's why this is the thing. When you are using this one, we are getting X hat. Corresponding this X hat, the system has a solution. Generally, suppose you take row space. It's a row space in Rn. Row space. See, we are taking linearly independent vectors. N linearly independent vectors. Okay, when that n linearly independent vectors means n linearly independent vectors, what is the null space? Null space of A is 0. There is no null space. Null space is 0. Suppose it is solvable. See, we are taking row space in Rn. That means we are taking A is a m by n matrix. Here m is more than n. That means it's not solvable. When it's solvable by projection, p equal to capital small p equal to A X hat. So that means we get column space. Column space. What the column space is? Projection. P equal to capital P B. Column space in Rn. in Rm. So now it's uh, solvable. Suppose where x hat, that means x hat is this one. Suppose it's not solvable, that means its system has no solution. No solution. X equal to b, no solution. It's a no solution means no solution that b is outside of this one. When it's outside, brother. Okay. So, it's outside. Suppose b is outside of this one. That means we get b is outside. We have to project to this b vectors to in this column space. And when that project, we get some error also. Error is in the column space. This is the orthogonal. This is error vector in the left null space. How to write this one? Okay, you write. Okay, the column space is this is the left null space of A transpose. A transpose. Yeah, this is the E error vector. Error vector lies in the left null space. See, that means B projection plus E. Already we know. What the B minus P. Now what the B equal to? E plus P. That means when it's not solution, it's divided to that error vector and 12. When that error is approach to 0, that B lies in that column space. That means this system, that one is a solution. You can this is just this is a row space. Only that we take n linearly independent vectors. That means the null space is 0, only 0 vector. Only that is the 0 is the common, the row space and the null space. See, it's not solvable. So, suppose it's solvable means that p equal to x hat. That means the projecting one. When that project we get column space. Convert to column space. That p equal to this p is the capital P is the projection matrix. The column space in Rn. So it's not solvable. That means the system has no solution. That means the B is outside of this column space. B is outside of the column space. That means you have to project to B2 in the column space. In that project we get some error. That error vector is lies in the left null space. This, yeah, this is left null space and the column space is the orthogonal. We know this any transpose orthogonal to column space of A, and these are orthogonal complement also. Left null space orthogonal complement is column space orthogonal complement is left null space. Already we discussed. Yeah, this is the thing. This is the way. Suppose take example. Okay, example. Suppose x plus y is equal to 0 and x minus x plus y is equal, x minus y is equal to 1. 2x plus y is equal to, so you take 2, this is the 1. Suppose take this three equation and 2 unknowns and 3 equation. The system is about right ax equal to b. That means a is the 1 1 2 1 minus 1 1 and xy equal to 0 2 1. This is ax equal to b. So now if draw the lines, what that means, this is the y is equal to minus x. This is the y is equal to x minus 2. Whatever this one, y is equal to 1 minus 2x. Now draw this graph. Yeah, y is equal to minus x means like this one. Y is equal to minus x line. Now y is equal to x minus 2. When is the x is 0, y is minus 2. Y is, when is the x is 0, y is minus 2. Write the 1, 2. When x is y is 0, x is 2, like 1, 2. That means you get graph line this one. Okay. Now see another line, y is equal to 1 minus 2. When the x is 0, y is 1. Like that. When is y is 0, x equal to 1 by 2. Somewhere. When x is 1, what the y is minus 1. Like this one will get. Like this, not intersecting this one. So now observe here, these three lines are not intersecting. It is one point. That means the system has no solution. Now how to find the solution? See now multiply. Take this one. Now take normal equation. Normal equation means A transpose Ax hat equal to A transpose B. That means A transpose A. A transpose means 1, 1, 2, 1 minus 1, 1. A 1, 1, 2, 1 minus 1, 1 into x hat. You can take x hat y hat equal to A transpose. It means 1, 1, 2, 1 minus 1, 1 into B 0, 2, 1. Now multiply this one. This equal to, now multiply this matrix. 1 into 1, 1, 1 plus 1, 2, 2 plus 4, 6. Now 1 minus 1, 0, 2. This must be get 2 because A transpose A is symmetric. You can check it. 1 minus 1, 0 is 2. 1 plus 1, 2, 2 plus 1, 3. This one. X hat, y hat. 0, 2 plus 2, 4. Now 0 minus 2 plus 1. Minus 2 plus 1 is minus 1. This one. So now the system is non-homogeneous system. Write the augmented matrix. What is the augmented matrix? 6, 2, 2, 3, 4 minus 1. Or you can go for any method. Solve this system. You can using any method. This equivalent to converted to this 0, 6, 2, 4, multiply with 3, 0. That means apply R2, 2R2 3R2 minus R1. 9 minus 2, 7. Minus 3, minus 4, minus 7. Is it correct? 9 minus 2, minus 3, minus 2. This one. Better to convert to row reduced diagonal form, get direct solution. Row reduced diagonal form. This is divided with 1, 1 by 6, 2 by 3, 0, 7. With this also can minus 1. I am applying R1 is R1 by 6, R2 is R2 by 7. Now convert to this 0, 1, 0, 0, 1. What is the one? Now to apply R1 is R1 minus R2 divided by 6, 0. So that means 2 by 3 minus 1 by 6 minus plus 1 by 6. How much? 5 by 6. 5 by 6 minus 1. Therefore, when you are writing equation, therefore x1 equal to x hat equal to 5 by 6 and y hat equal to minus 1. The solution is the solution is x hat equal to x hat y hat. This is 5 by 6 minus 1. Now observe here 5 by 6 minus 1. Where is the 5 by 6? 5 by 6 means 5 by 6 and minus 1. Minus 1 means y is minus 1 somewhere. Minus 1. So okay, we are taking minus 1 and 5 by 6. 0 point something. X is 0 point something. Somewhere like this is the one. And now we are getting this lines are the solution point is like approach this three equation solution. You get best solution is here this one. This is the system has no solution, but the you know take this system this one, or you can project that one. Suppose we have taken here x equal to b. Now this vector 0 to 1. Suppose for example, whatever taken. Suppose a1 or the a1 1 1 2 1 1 2 b is no, a2 0 to 1 1 minus 1 1 a2 is 1 minus 1 2 the b equal to 0 to 1 0 to 1. See now just I give idea what that means. Suppose in the now writing the vectors a1 a2 and b, this is the matrix, this is the matrix a columns with a b vector. Suppose that means b vector is not in column, b vector is not in column, b is outside of that vector. Try this problem. Suppose you take any vector, suppose a1 a2 in the column space a1 a2. Now this is the b vector. Now project b2 on the column space. Suppose column, this spanning some vector. Suppose I am taking the vector is like now project this vector to on this column space. See now when that projecting this vector somewhere is like this vector. If this vector is projected to this one, this we get some error. The projecting. We'll see how much error hides that error. If we get error, it's not we get some error. Suppose there is no error means the b is lies in that column space. But here this system has no solution. That means it's outside of that row space. Now by projecting it convert to this is in the row space. The using this normal equation. We are using this algebraically a transpose a x hat into a transpose x b. This is the algebraic equation. Geometrically that means we are projecting b2 in that column space. This is the one. Now try one more problem. Solve example. Okay, solve this system. So this system x plus y is equal to 0, x minus y is equal to 1. Okay, I think here is 2x minus 1 equal to 2, x minus x plus 2y is equal to 1. Solve this system. Yeah, this means 2 unknowns, 4 equations. This system has no solution. Now you can draw geometrically there is no intersection point. This 4 equations. Now what is the best solution for this system? Try this way. But here I am written this a1 a2. 1 minus 1 1. 1 minus 1 1 not 2. That I did. See next class we discuss how to fit a line and parabola curve. So now I am stop here. Thank you.